Hello everyone, welcome back to my channel. Suhail this side. So this would be the first video in the multi-threading Zero to Hero series. So in this series we will be learning from basic to advanced concepts in the multi-threading, like how we can prevent race conditions, how we can do thread synchronization, and how we can do performance tuning if we have many more threads. And this all learning would be based on practical with the real code examples, right? So without wasting time, let's get started. So today's agenda would be, we would be understanding what are the processes and what are threads and what is the actual difference between the process and threads, right? Then we will see how the scenes, we will see all this with the real code examples. So I will show you in the code where actually the operating system plays the role, right, with respect to code. So we will see the context switch with the real code example, right? So I have written a code at which point the context switch would happen. I'll show you there with the code example. Then we will see the memory management with respect to process and threads. So at the last we will see what is the difference between concurrency and parallelism. Many of the engineers doesn't know the difference between concurrency and parallelism. We will discuss all these topics in detail. So let's get started. So first of all, let's understand how operating system works at very high level, right? Because this is very important to understand the behavior of threads. If you don't know how operating system works behind the scenes, you won't be able to solve the issues which comes in the production. Because generally in the production, what kind of issues would come, you have to deduce from the logs, right? So at that point of time, if you don't know this basic, right, so at that point of time it would be very difficult to solve those issues. So operating system, how it works behind the scenes, is very crucial for understanding threads, right? Let's get started. So if you see the diagram, I have taken this diagram from the Wikipedia. So if you see the diagram, so it is clearly mentioning all the components here, right? Now let's imagine you have built a simple Java application, right, or any kind of application, either Java application, Python application, any kind of application. When let's take an example of a Java application, right? So how you build the Java application, at the end of it you get a jar file, right? Now where does the jar file would place? It would be placed on disk, right? It would be placed on hard disk, right? Now the jar would be placed on disk, but it has the program. And what is the program? Your program is nothing but a sequence of instructions, as you see in the diagram, right? Your program is a sequence of instructions to execute. Now when you run the Java program, how you run the Java program? You just do the java-jar myapp.jar. Let's assume my app is the jar name. Then what would happen? Then a process will be created in the memory, right? If you see here, the process is created in the RAM, right? Now the process is created in the RAM, it doesn't mean it is in the running state, right? So let's understand actually what is a process. So process is what? Process is an instance of computer program, right, which has its own isolated memory space. Now process has its own memory space, right? It will include code, data, and other resources allocated by the operating system, like memory, socket, and much more, right? So when you write the Java program, right, so for example, the process is instantiated, right, but it has the set of instructions to be executed, it has the code, right, it has the data, right, all these things it has, right? So all those things, where it will reside? It will reside in the RAM, right? So process is very heavyweight, it lives in the RAM. It doesn't mean it is executing. CPU, what CPU actually understand? CPU actually understands the instructions. It doesn't know about the process or thread. What CPU is executing? CPU is just aware of the instructions, right? Now if this is a process, what is a thread? thread is a part of process, right? A process, for example, this is the process, and these are the three threads. A process can contain one or more threads, right? And all the threads within the process can share the same memory space. Let's assume the pink color here, it represents the memory space. So all the threads within a process can share the same memory space, right? So in simple terms, if we see here, right, if we see the diagram here, so we can clearly say process is a unit of resources, right? In simple terms, CPU doesn't understand what a process or thread is. CPU understands the instructions, right? And a thread is a unit of execution. Why? Because each and every process would have one thread, at least one thread. For example, if you see in the diagram, these are the thread available there which has to be run by the operating system, right? I will explain in a more deep manner as and when we are going further, but just looking at this diagram, right? So if you have threads, thread has what? Thread has set of instructions which needs to be executed, and each process has at least one thread, right? So operating system scheduler schedules the threads and assigns the CPU to it, and then finally CPU executes the instructions, right? This is how the process is. Now let's dig more deep what actually all is about. Let me show you the example. I'll show you the example as well. For example, I'll show you the activity monitor. If you see the activity monitor, this is an IntelliJ IDEA, right? Now how many threads it has? It has 135 threads. So each process has at least one or many threads, right? Now so that is all about the process. Now let's understand what is the context switch. When you have so many threads, or when you have so many threads, now operating system has to select which thread has to be executed by the CPU, right? So when you have multiple processes, for example, you have IntelliJ IDEA, Java application, etc., or any kind of other applications, each and every process has some kind of one or multiple threads. Now what would be happening? All threads would be competing for CPU, right? Now all threads would be competing for CPU as shown in the diagram. These are the threads which are there. All the threads needs to be run, but it needs CPU to run, right? Now what would happen? So if all the threads need CPU, so how the process is happening? So a OS scheduler will keep on switching among the threads for the execution, right? So it doesn't mean that, for example, if there is a limited CPU resources, right? It doesn't mean that if you have 100 threads, all the 100 threads would run in parallel, because CPU has limited resources. It can run only one. If assume it is a single core CPU, then it can run only one single thread at a time, right? So operating system has to switch among the threads. For example, as of now this thread 1 is running, and once that after some time interval thread 2 will get a chance to run it. Who will select thread 2, thread 3, thread 4, and which thread is to be executed? The operating system scheduler would select the thread, which thread has to be executed, right? So this is all the context switches. Now you would say, okay, when it switches from one thread to another thread, right? Now the current thread execution point, the state, it has to be stored somewhere, right? Now when the switching has happened, so the current state has to be stored somewhere. This is where the stack comes in picture, because next time when operating system schedules the same thread again, it has to be executed, it has to be run from the instruction where it has left, right? So that is very important to store the current state of the thread, so that next time it can be resumed from the point where it has stopped, right? Now let's see the simple flow, how the flow would be. Assume this is a process and we have 3 threads, and this is kind of operating system scheduler, right? And assume we have a single core CPU, right? Now your operating system scheduler would assign one of the thread to the CPU, right, for execution. Now, who will decide for how much time this CPU should execute this thread? The scheduler will decide. That is where the operating system algorithms comes, like the preemptive scheduling, the round robin scheduling, the time slice scheduling algorithms. The operating system scheduling algorithms comes there. So the operating system scheduler has different kind of algorithms according to which it will decide for this much time this thread should be given CPU, and for this much time this thread would be given the CPU, right? Now let's assume at T0 point this black color thread has been selected and assigned the CPU, right? Now after some time, what would happen, since there are three threads and how many cores are there or how many processors is there? This is a single processor, right? Now if it is a single processor, only one thread can be executed at a time. So for other threads to be executed, what operating system has to do? It has to switch. It has to switch among the threads. It has to take take this thread and it has to take this thread and it has to, for example, it has to take this thread and park it somewhere, and it has to run the this one green one thread, right? So this is how it is happening, right? So when you have one processor and multiple threads, it will switch among multiple threads, right? The operating system would keep on switching the threads. So modern CPUs have multiple cores. Now each CPU can have one core. If you have to buy laptop, if you have seen your current laptop as well, you must have seen a one core CPU or two core CPU. Nowadays there is no more one core CPU, but 4 core CPU, 8 core CPU, 16 core CPU. So each core can be seen as a different processor. Now how many cores are there? That many threads you can schedule. The operating system can schedule that many threads. Now let's understand all this with the code example, right? Now let's understand this code example. Let's assume this is the code which has to be executed by any kind of thread. That let's assume any kind of thread which is executing this application code. Now when Java thread executes this code, right, but you have other threads also, right? So the operating system scheduler would keep on switching threads. Now for example, this thread is currently calling foo, then from the foo it is calling bar, then from the bar it is calling test, right? So the operating system has to store this method specific local variables. For example, int a is equal to 10. This has to be stored somewhere, and the functions calls also has to be stored somewhere. We call that memory is the stack memory. So usually what happens is we have two types of memory, that is heap memory and the stack memory, right? So where does the heap memory comes in picture? Heap memory comes in picture when we dynamically create new objects. For example, when we do new object, right? So at that point of time, what would happen? This object would be created on heap, and this obj reference would be placed on stack. So stack contains local variables, object references, and function call information, right? Now let's see further. Now this has all this information is stored in the stack, right? Now each and every thread, for example, this is a process, right, and these are the three threads, right? Now each and every thread has its own stack memory. For example, this green thread has a green stack memory, the orange thread has a orange stack memory, and so on, right? So each thread has its own stack memory, right? Now you would ask, okay, if the stack memory is being assigned by each thread has its own stack memory, who will determine the size of stack memory, right? This could be your next question, that what could be the size of stack memory, right, for an individual thread. Okay, so what happens is actually it has to be given upfront when a thread is created. If we don't mention it, by default every language what assigns is some kind of default memory to each thread. For example, in case of Java assigns 1 MB stack memory to each thread, right? It all depends on CPU architecture, what kind of operating system and CPU architecture you are using. But okay, you would say, okay, so if Java is assigning 1 MB, can I change this stack memory? It could be possible that I need to do some more CPU intensive computations, right? So in that case, I might need to have more stack memory, right? But yes, you can definitely do that. Either you can decrease or increase the stack memory using the XSS flag. This is the flag which is available in the Java. Using this you can control the stack space, right? And the other thing is, by default what happens is you can change this stack space in the Java process. You can just pass this argument. Now what would happen, for each and every thread this many memory would be assigned, but you can still override this stack memory. How? Programmatically. For example, in some of the distributed applications and or some of the high-end applications, usually to support high concurrency, right? Because you might need to handle so many IO requests. Those requests are not kind of CPU intensive but kind of IO requests. In those cases you might not need 1 MB stack, right? Because if you are creating 1 MB stack, it would be a lot of memory consumption and lot of memory wastage, right? So if you go further into the distributed systems, many of the systems tweak this setting. For example, if you have to tweak this setting in Java, you can just, there is a one parameter in the thread class available. For example, in this example you can see here, I have just created the 256 KB stack for this thread. So for this thread the 256 KB stack would be allocated. This is the Java example. Now similar example could be seen on the Python example, in the Python language. So in the Python you can just specify at the beginning the stack size. By importing the threading module you can specify the stack size is 256 KB or whatever based on your business load, and at the end you can just create the thread and start it, right? So with this your stack memory would be increased or decreased based on your business load. Okay, now the next question would be, do we ever need to change the stack size? Yes, as I said, many of the real world applications which support large concurrency usually tweaks the size, right? But it all depends on the use case. For example, let's take an example of web servers, right? Web servers like Apache Tomcat or Jetty or Netty, which can handle thousands of concurrent connections, right? Now for this concurrent connections you don't need kind of that much heavy stack. These are kind of IO requests, right? Each request might create a thread, right? And if just assume that if 1 MB stack is being allocated to each and every thread, right? So 10,000 threads, how much memory would require? It would require 10 GB of memory, right? So this leads to out of memory error or excessive GC pressure. So the garbage collection would also happen at the background, right? And lot of garbage collection would be happening, and your Java application might get paused for some time when garbage collection is happening. So this will automatically reduce the performance. So what is the recommended solution for this? Because since this is a kind of IO request, we can simply reduce the stack size. For example, based on our request 256 KB or 512 KB, though with this we can handle the double or twice or 4 times concurrent users on the same hardware, and also the memory footprints would be reduced. Now okay, you would ask, okay, now we have talked about stack memory. Well, what about process memory? How much memory is being allocated to process? Who would determine this thing, that how much memory has to be allocated to this process? Okay, now in every language you can control this process memory usage. For example, in Java, that is depending on XMS and XMX parameters. XMS matlab means this will set the initial heap size. For example, with the attribute of XMS, right, it would require 512 MB at the beginning, and as and when your application needs more memory, it will go till the point your maximum memory can be reached, right? For example, the maximum memory I have specified here is 2 GB. Now if the process needs more than 2 GB, you would see the out of memory errors, right? So that's how the process gets the memory. Every language, in whatever language you are developing or writing the program, so every language has this setting. So based, it doesn't like that you have just scheduled the process and it will run indefinitely. If that would be the case, all the other processes would not able to run. So all the physical RAM of the operating system would be kept by a single process. So there is no one in the world do like this, right? So what actually happens in every language or whatever the kind of process or whatever kind of application, in every application they have the process control parameters, memory usage parameters. For example, as I mentioned, in the Java we have this, in the Python we have something else, right? Now how do we evaluate how much memory should we give to process? Okay, so how you come to this number that xmx should be 2 GB, the maximum heap could be 2 GB, not more than that or not less than that? How you would evaluate that? Okay, the minimum memory should be 512 MB. How much, how you calculate this number? This is a very important interview question as well, right? So what happens actually, that all depends on what your program is doing. If your program is, for example, let's say some kind of cache service, it obviously needs more memory. That means the object should live forever in the memory till the process is live, right? Because you need some kind of you don't want to hit to the database again and again. That process has to be live in the memory, right, forever, so that the performance can be increased and latency could be decreased. So right, so how you usually calculate this number, that what would be the minimum and maximum value? You actually, in the real organizations, do what you do, you do the load testing to generate that amount of data, right? So you generate the you simulate the load and you generate that kind of data your application should handle according to the use case, and based on that you get the actual number which would be safe to run in the production. So this is how you would get this number. Now let's understand the system calls with respect to multi-threading. Why I am going this much deep? Because when you will go in designing distributed systems, or when we will go into the other series, the HLD series from zero to hero, there I will be talking about all these concepts. The system calls is happening, right? So in distributed system, this is very, very important to understand all this actions, what actually is happening at the operating system level, right? Now internally what happens, actually everything is happening via system call. Now let's assume you have any kind of application, right? So any kind of application, that's a user space, right? Whatever you see on your system, it's a kind of user space, right? Now what happens is, you have written a Java program you have written, and you have the Java program is resided on the disk that is there. Now when your process is instantiated out of that particular program, right? So what happens, for example, your process is internally reading the file, right, or internally doing some kind of network calls to the other service. So what happens, it all happens via system call, right? So your application internally calls system, do the system calls to the operating system, and the operating system then calls the hardware resources. For example, in case of threads, the operating system has some kind of scheduling algorithms, which on the basis of which the threads would be scheduled and the CPU would be assigned, right? Now for example, let's take an example of the thread. What actually happens when you create a new thread? When a new thread is created in the Java, for example, the new thread dot start. So I'm just taking an example of Java, but you can assume this all happens in the same, all the other language, the process is still the same, right? So what happens is, the Java program requests to create a new thread, right? that's done. What would happen? The JVM would make a call to the would make a system call to the operating system kernel, right? So operating system call would be made to the operating system kernel. Now what all the calls are there, the kernel already expose all these APIs, the pthread or pthread create or clone. These are the APIs which have been already been exposed by the operating system. Now for example, if you see the Java, there you have the DLL files, glibc or libc kind of files that internally makes the call to the system, that internally make the call system calls to the operating system. For example, glibc or libc, right? These are the, or the JVM DLL, right? These are the files you must have seen while in the JDK or JRE environment, right? In the, when you have the JRE, so you see these files. So these files internally calls the system calls to the operating system kernel level, right? Now what operating system has? Operating system has the thread scheduler. It will allocate CPU time, manages the context switches, assign stacks and registers, and all the low level APIs, for example, which I have already mentioned, the clone and the pthread create. These are the kind of APIs which have been exposed by the operating system, and Java calls all these APIs through this libc, glibc, all the kind of the internal libraries, right? Now what are the key takeaways out of this? So key takeaways, your Java code, for example, thread.start only request a thread. The kernel space actually, OS is actually creating and manages a thread. JVM is just acting as a bridge and calling system functions to create and manage threads. So this is all we have understood, right? Now let's deep dive more. What actually is the process and the thread? Now, as I mentioned, let's assume this is a process, and what happens in when you run the Java application, Java what on what the Java application usually run on the JVM, right? So process has the JVM, right? So that is there. Now if you have written the code, your code has to be loaded into the RAM, into the memory, right? Now where the code would be resided? In the code segment. This is a just a block diagram I am mentioning with respect to process and all the internal components of the process and the thread. So let's assume these are the thread, for example, thread 1, thread 2, right, thread 3, right? These are the threads. All the threads share the same code segment, data segment, and also share the same heap area, right? For example, the code segment is already there, the code is already loaded into the code segment, right? Now the thread is just actually pointing to the thread is what? Thread is a set of instructions which needs to be executed. Each thread has set of instructions to be executed. So every thread has a counter. Now counter, what happens? It points to the instruction which has to be executed, right? It's a kind of program counter. So it points to the instruction which is executed, right? Now every thread has stack and the register as well. Now you would ask, okay, why you did not mention about stack, you did not mention about register, you earlier you just mentioned about stack, right? Okay, now what happens actually is registers are the fastest memory unit for the process or for the thread, right? So what register hold is, register hold temporary data during execution, and register help us in the context switching. The purpose of register is just in the context switching and in the you can say in the holding the temporary data execution. Now you see this is a process and this is a CPU. When thread is assigned to a CPU, now CPU is doing some kind of logic, right? Calculating or doing some things, right? Or for example, addition of two numbers, so it is also doing something. So where the CPU would keep all these calculations or keep all these values, right? So will it store in the thread directly? No, because then it would be quite cumbersome, right? So what actually CPU also has registers, right? In CPU also, registers serve as a temporary storage locations that holds data and instructions that a thread is actively working on. Now the active working thread, whatever the active working thread is doing, that would store in this register, right? Now you would say, okay, what is, let's see the difference between stack and register, right? So stack actually stores the function call history, which we have seen, the function call history, the stack frames, the local variables, the return addresses, and all this. What register holds, register hold the temporary data, addresses, the execution state of the current thread, right? No, each thread has its own stack maintained separately. Each thread has its own set of registers as well, but registers helps in the context switching. We will go through the code example as well, where the registers would come in picture and where the stack would come in picture. Now let's see the code example of this. For example, this is the code example. Now if you see, this is a one thread, the task is a thread. You can consider in any language, it would work in same way. Now what would happen is, in the run method I have declared int a is equal to 10, b is equal to 20. Now where it would be stored, when the thread would be scheduled, when the thread would be executed, right? Or so it would be stored in the thread register, right? It would be stored in the thread register. B is also would be stored in the thread register. Now let's assume after this point we are making a function call, addition of two numbers, the add a comma b. Now this would be a function call. Now what would happen? Now it would create a new stack frame. So this would create a new stack frame, and in this method what we are doing, we are just calculating the sum is equal to x plus y. Now where would this sum would be calculated and where it would be kept? It would be kept in the local stack, that is the in the stack frame, right? Now once this method is completed, when we are returning the value from this method, what would happen? We would store this value in the register before saving to the memory, right? Because it could be possible that just after the add method, this thread has been switched, this thread has been context switched. It could be possible that in the, for example, in this in the run method, at the end we are printing the result, right? It could be possible just before printing, this thread has been switched. But do you think that the add a comma b would be called again? No, because it has already been executed and already been executed in the stack, but the result has to be stored in the register. This is where the register would come in picture, right? So what, let's see the flow. Register stores temporary values, the a, b, sum for fast computation, which I already explained. The stack stores the function calls, all the function calls which we are making, that would be stored in the stack, and all the local variables would be stored in the stack. We need some kind of differentiator other than register to do all this calculation, or to do all this you can say to do all this computation, right? Because if all this computation is being happening on the register, it would corrupt the register memory location, right? So you can understand that how important is it. Now each thread has an independent stack, right, ensuring isolation. So each thread is performing on its own stack. Now during context switching, register values are saved, as I mentioned that, for example, just before the print statement, the thread is switched, right? Now all these register values are saved and restored from the thread stack. Now later on, when this thread gets scheduled again, it would see the register, it would load the register into the CPU register, it would load this register, right? It would load this register into this CPU register and print the value that it would done. So that is where the thread register and the stack register would come in picture. Now let's see the example of code context switching. What actually is context switching? For example, let's assume this is the code that it's a run method, right? In this run method, what we are actually doing, we are just printing the value, right? We are just printing the value, but just see here, I am just doing the thread dot sleep, right? I am just thread dot sleep. What would happen in this case? It would make the thread in the sleeping state. So what would happen? The CPU would be idle in this case, right? Now when operating system will see, okay, that CPU is idle, but there are other threads which are there, which has to be scheduled. Now what operating system would do? Operating system just schedule the other thread and would switch this thread and would run with the other threads, so the other threads also get a chance to run. Now let's see the flow for this. Each thread runs independently. For example, I have created two threads, thread 1, thread 2, and I have started two threads. Each thread runs independently, executing its own set of instructions. No registers are actually, for example, this register value is equal to 0, right? So I'm just simulating these values because it would be stored in the register, because when the context switch happened, so the register values would be loaded and the computation would be performed from there on, right? So registers are maintained separately for each thread. Thread dot 500 sleep 500. I'm just doing this for what purpose? For just doing the context switch, just to allow the operating system to switch among the threads, so that the output will interleave between, because the JVM and the operating system decide when to switch threads. Now if you see the output, you would see, okay, that all the threads would have its own value. There is no there is no race condition over here. So that is how the context switch is there. All the values are local to this particular thread, and because how it is local, because all the values are stored in the register, right? So that's how it is. Now let's understand the concurrency and parallelism. So this is where many of the developers struggle. What actually is concurrency and parallelism? Now we'll just understand this concept with a very simple example. Let's assume we have a web server and we have a client, right? Now you make two requests to the web server. Let's assume task 1 is to handle request 1 and task 2 is to handle request 2. You created one thread for every request, right? So task 1 represents one thread and task 2 represents the other thread. Now imagine you have a single processor machine with a time slice scheduling algorithm, right? Because how it happens, the operating system has the scheduling algorithms, right? So assume each task is scheduled for a fixed length time slice and then is preempted. Who will select that this thread has to be preempted and the other thread would be rescheduled? The operating system, based on its algorithm, right? Now let's assume this is the timeline for the all the tasks, right? Now the time span is start to finish. This is the start and this is the finish. Now you have a single processor. No, but you have two threads, the task 1 and task 2. What would happen in this case? What would happen in this case? In this case, task 1 and task 2 would share the same processor, right? So task 1 and task 2 are processed concurrently during this time span. Their processing overlaps during this time span, right? Now but if you see here, task 1 and task 2, they are not running in parallel. Although you have two threads, but they are not running in parallel, right? So this is concurrency but not true parallelism, right? Now let's assume the second scenario. The second scenario is you have multiprocessor machine. Assume there is a dual processor, right? And if you see, the task 1 is running, and when you get the task 2, it would also be starting running on processor 2. In this case, if you see, you are achieving true concurrency and you are achieving the true parallelism, right? So with this approach, your machine throughput is improved. Task 1 and task 2 both are completed faster than the first case. Now key takeaways. What are the key takeaways out of this? Concurrency and parallelism are different. Concurrency involves handling multiple tasks in the same time span. Although you have the two requests at the same time, the task 1 and task 2, you got the two requests exactly at the same time, but actually these are not running in the parallel. Parallelism involves processing multiple tasks literally at the same time. True parallelism requires multiple processor, right? But okay, you would say, okay, no, but there is one point to note: some languages prevent parallel execution of code. For example, in Python you have the global interpreter lock, right? That Python GIL prevents true parallel execution of Python code, but IO bound operations, for example, the network request, file IO operations, reading and writing the file, you can still use multi-threading there in the Python. Who said you can't use the multiple threads in the Python? You can use the multiple threads if just only for the IO operations, but you can't use the, if you are doing the multiple, if you are using the threads for the CPU intensive tasks, at their Python internally will run only one code. It won't run in parallel actually, right? So your machine throughput would not increase in that case. But yes, of course, if you have IO bound tasks, you can use multiple threads in the Python as well. No, that was all about. Now let's discuss all the summary and the advantages and disadvantages what we have studied till now. Now, as you have seen, Java and Python threads are just a wraparound OS thread. Now, Java was invented close to 20 to 25 years back, right? Now, one Java thread is equal to one operating system thread. This statements is true till the virtual threads doesn't come in picture. Now with the virtual threads, this statement is not completely true, because there are two types of thread: platform threads and virtual threads, which we will discuss later in the series. But just remember, one Java thread is equal to one operating system thread, and it happens in the same all the languages. Most of the languages, one Python thread is equal to one OS thread. Why is it so? Because OS thread is what is actually the unit of scheduling, right? The operating system thread is actually, as we have seen here, right, in the system calls. Now what happens is, the user program starts the thread, but internally when it calls the system call, the operating system is what actually creating the thread behind the scenes. So operating system, who will schedule? The operating system will schedule the thread which is created by the operating system, which is created by the kernel. So Java thread is just a wrapper on top of it, right? So let's discuss the advantages and disadvantages if we are using multi-threading. Now what are the advantages of using multi-threading? Of course we have the improved CPU utilization. Multi-threading helps maximize CPU usage by running multiple threads simultaneously, which is obviously preventing idle CPU time. Right now you can see the faster execution, parallelism, which we can achieve. The asynchronous execution is the most important in distributed systems. You for most of the IO tasks, you can see the threads are being involved there, right? So multi-threading allows asynchronous operations, meaning tasks can continue without waiting for others to complete. For example, downloading a file while allowing the user to interact with application. This is a kind of an example. Now what are the disadvantages? Disadvantages could be, if you are using multiple threads, there could be a complexity in synchronization, right? You might need to handle deadlocks, race conditions. You have to be careful, and you have to use synchronization mechanism, for example log, semaphore, atomic variables, and much more. Then the debugging would be kind of difficulty. From the logs you have to prove, okay, that you have to just think or visualize or elude, okay, that this would have happened, this thread would have done this way, this thread would have run till this point, and after this point this thread would have been scheduled, and that's why this is the race condition. So debugging is much difficult in case of multi-threading. Then the other point is high memory usage. As I mentioned, the every thread requires a stack memory, right? So by default Java assigns 1 MB stack to each thread, right? It completely based on your use case, but if you are spinning more threads, right, it may lead to out of memory error or thread contention. So you need to be careful about this as well. So what are the what the other disadvantages could be? You are more prone to deadlocks and thread starvation, because if you have more threads, this it all depends on operating system which thread has to be scheduled. Uh, the thread can be starved for a long duration, right? So the thread can wait indefinitely while the other threads keep on getting the chance or keep on getting scheduled, right? So these are the problems which you might face if you are using multi-threading. So you have to be very careful, and you have to use all the synchronization mechanisms. You have to be careful of all these scenarios. So that was all I had planned to cover. So believe me guys, this would be the in-depth and real practical use cases based series, and we will discuss much more scenarios like doing the performance tuning, how to prevent race conditions, how to do thread synchronization, and much more, right? So that's all, and see you next video. Thanks a lot. Thanks.